So as a natural follow-up to our videos on U substitution, we're going to dive into this topic regarding doing integrals that involve purely trig functions. And so before we even really get started, or before we can even get started in this video, we need to remember a couple of identities involving those trig functions that maybe you've seen in the past. So some good old-fashioned trig identities that we're going to want to have in our back pocket. And I would say at least the first two are identities that you're expected to know without looking anything up. Although you will find that if you go into the course, into the Canvas course and look in files, you will see a file that has trig identities there to kind of help you. But I would say, for anyone who has to keep going in math, these are a couple identities that you're going to need to know really well. So the very first one is the classic trig identity, sine squared of theta plus cosine squared of theta is equal to 1. That's very classic. The second one you can get by manipulating this one a bit. So for instance, if I were to divide everything on the left side and the right side by cosine squared theta, if I were to do this, then what's going to happen is I'm going to end up with sine squared over cosine squared, which is tangent squared of theta. And then I'm going to get plus cosine squared over cosine squared, which is just 1. And then on the right side, I have 1 over cosine squared, which is famous for being secant squared of theta. So for starters, we're going to say these two identities, this one here and this one here, are the two that we really want to know really, really well, kind of going forward in this class. And they're, again, like you really only have to know one of them because you can derive the second one from it. But maybe we'll say an additional one are going to be a couple of the double angle identities. So for instance, or maybe like a power reduction identity. So maybe if we were given, sine squared of theta, what does sine squared equal? Well, on the one hand, I could rearrange this and get that it's equal to 1 minus cosine squared. But it turns out there's another identity, 1 minus cosine of 2 theta all over 2. All right, there's an identity. And kind of a partner identity for this one is also that cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. Okay, and there's a whole bunch of identities that are going to be pretty useful and they're good to know for if we start hitting roadblocks with integrals that involve trig functions like we are going to be working with right now. So maybe I'll just kind of, put these off to the side for a second and we'll kind of continue on with this video. And if we need those identities, we are going to come back to them. So the very first type of trig integral, right, what am I talking about? It's exactly like what it says in the name. It is an integral that only involves trig functions. So for instance, something like this, how do we go about doing it? Now, as this video follows the U substitution video, I am hoping that at this point you have seen U substitutions and you have some idea that we can identify that here I have sine, its derivative is cosine, and so I could say, let U be equal to sine of x, and then what are we going to get? We're going to get that du dx is equal to cosine of x. And so this immediately is going to give us, well, we can do a little bit of algebra anyways, that du over cosine of x is equal to dx. And so we can solve this not too bad because we're going to get sine of x, not sine of x, we did a u substitution, so u times cosine of x, and then times the dx that we just came up with, which is du over cosine of x. And that's just the integral of u du, which in and of itself is u squared divided by 2 plus c. And if we go back to xland using our u substitution, we get sine squared of x over 2 plus c. And voila, we have achieved the solution to this problem. But now let's try and modify this just a little bit. Let's see what happens if we have the integral of sine of x times cosine squared of x. Right, what happens if we have something like this? Because, as we practiced in the last video, we cannot let u be equal to sine of x here. And the reason is because we're going to get that du is equal to cosine of x dx, which is only going to cancel out with one of those cosine of x's. We're going to have one left over, and it's not going to work. And if you're unsure of that, you can divide both sides by cosine here, plug it in specifically to your dx, and you're going to see that it just doesn't work for us. So we're going to have to abandon ship. But as in the last video, right, if one of them doesn't work, maybe there's something else that works. And so in this particular case, we're going to let u be equal to, now we're not going to select cosine squared, because if we select u equals cosine squared of x, then the derivative du dx would be, we have to use the power rule and the chain rule, right? We'd have 2 cosine of x times the derivative of cosine, which is negative sine of x. We have too much stuff coming out here. We're going to be left over with this extra cosine that we're not going to know how to deal with. So we can't pick u is equal to cosine squared of x, but we can pick that u is equal to cosine of x. And this is going to give us that du dx is equal to negative sine of x. And so if with a little bit of rearranging, we're going to get negative du over sine of x is equal to dx. And this particular one we can now solve because we'll have an integral with sine of x times u squared times our negative sine, negative du divided by sine of x. Like so, the signs will cancel. We can pull the negative out front because it's a constant, it's -1, and we're just doing the integral of u squared du, which becomes u cubed over 3 plus c, and our final answer, going back to where we started, would give us a negative, what's our u? Cosine? So negative cosine cubed of x over 3 plus c. And again, you can always check your answer, right? If I were to take the derivative of this, the 3, we would drop down. It's going to cancel out with this 3. So we're going to get 3 cosine squared. That's going to give us this bit. And then times the derivative of the inside, the derivative of cosine is going to be a negative sign, which is going to cancel with this negative and get us back to where we're going. So it is good to take pauses and check your work and to, I guess, just make sure that you still know how to take derivatives. So this one wasn't so bad. Let's see, how about another one? So now let's dive into ones where things aren't as easy as just one simple u substitution. So for instance, what if I have the integral of sine cubed of x dx, okay? And now this one's a little different than the rest because there's no u equals that can happen, right? Because the derivative of sine is cosine, and there are no cosines in this problem. So there isn't just a substitution we can make. We can't just do the antiderivative. We can't just say this is like sine to the 4th, over 4, because this is a trig function. There's some chain rule business going on. It's not just x cubed or something like that. So we can't do any of that. But the thing that's going to inform us what to do is exactly what we said, which is, look, we could do a u substitution with this if we had like a cosine sitting around, right? And furthermore, we should hopefully know one of those identities that I brought up earlier at the beginning of class is going to start to make its presence known. And so this is going to involve a very slick trick, which is I'm going to split my sine cubed into sine of x multiplied by sine squared of x dx, because now I can go up and I can use my Pythagorean identity, specifically this one that says sine squared of x is going to equal 1 minus cosine squared of x. And now I have some cosines that are showing up. Now you might ask the question, you also have a sine squared equal stuff here. Why aren't you using that one? You definitely could try and do it. But I know the reason why I'm not is because my integral, which we split into sine of x times sine squared of x, if I convert this into 1/2 minus 1/2 cosine of 2x, right? So I take this, I split it into two fractions, I make that substitution. The problem is I'm going to have a sine of x and a cosine of 2x, and I would not be able to say, you know, let u be equal to sine of x or something, because the derivative is going to be cosine of x dx, not cosine of 2x. So this particular method doesn't work. I'm going to use the Pythagorean identity here to get my cosine to show up. So back to this problem, we're going to just rewrite this integral. So we have integral sine of x, and then multiplied by 1 minus cosine squared of x dx. Okay, so a bunch of ways to do this now, but I think the easiest thing is just going to be to distribute everything in. So we have the integral of sine of x minus sine of x times cosine squared of x dx. And now all of a sudden we can do this, because the first one, the antiderivative of sine is negative cosine, and the antiderivative of sine of x cosine squared of x, we just did up here, right? That one's just a quick u substitution, and we are good to go, because we can let u be equal to cosine, the derivative of which is negative sine, and life is going to be good. So at this point, we can pause and say, hooray, we have made some progress. Okay, so let's see, what other kind of trouble could we get up with into using trig functions? Well, we did sine of x times cosine squared. What if we do sine squared of x times cosine squared of x dx? Okay, what if we do something like this? And similarly, you know, we're going to say, well, I can't let u be equal to cosine of x, because the derivative would just be one of these sine of x's, right? It'd be a negative sine of x. But that means we're going to have a leftover sign kind of sitting there. I can't let u be equal to sine of x, because the derivative of that is cosine, and it's only going to cancel out with one of these cosines. So looks like we're in a little bit of a pickle. And so I think my first step, if I had no idea what to do, is I'd probably try and use one of those trig identities again. And I'm going to stick with turning sine squared into 1 minus cosine squared of x. Now, again, well, how do I know how to do this? I don't. I'm just experimenting. I've noticed that u substitution has failed us. Let's try going this particular method. So if I do this, we get the integral of cosine squared of x minus cosine to the fourth of x dx. And again, we run into an interesting problem, which is, I don't have anything to do a u substitution with here. Very sad. I don't have anything to do a u substitution with here. Very sad, right? These are technically two separate integrals that are happening at once. So I can't, just turn one of them into sines and start using a u substitution like that. It will not work. But what we can do is now we can use one of these half angle identities that we wrote up here. And so using this one is really good when we're doing an integral of just a single trig function where we want to do what's called power reduction. Okay, power reduction, which is the idea that I have to integrate sine squared. That's hard, but I know how to integrate cosine to the first. That's no problem. And so what we're going to do here is we're going to use that second identity. So what is it? It's 1 plus cosine of 2 theta over 2. So I'm going to write this as two separate integrals for now. I'm going to write this as the integral of 1 plus cosine of 2x all over 2 dx. And then for now, I'm just going to shelve the idea of minus the integral of cosine to the fourth of x dx. I'm just going to kind of put this off to the side over here. Okay, so let's deal with the one on the left. Now, thankfully, the one on the left just splits into the integral of 1/2 dx plus the integral of 1/2 cosine of 2x dx. The first of which just becomes 1/2 x, and the second of which becomes 1/2, okay, the antiderivative of cosine of 2x dx. So we're going to have to kind of finesse our way through this one. But we should have an idea that it's probably going to be sine of 2x. And then you can do this a couple ways. We could say, oh, I don't know how to do the antiderivative of cosine of 2x. We could do a u substitution, let u equal 2x. du is going to be equal to 2 dx, right? I could do a u substitution for this. It's not a bad strategy. But you could also use some intuition, which says that if I were to take the derivative of sine, I would end up multiplying this thing by 2 once I take that derivative. So if I'm taking the antiderivative, I would want to undo that. I want to divide by 2 to make sure that that kind of cancels out in the process. And that's the path that I'm going to do. A little bit of intuition here, which is going to say that the integral of cosine of 2x is just sine of 2x over 2. Again, you could check it. We're going to get cosine of 2x over 2, but then we're going to end up multiplying by 2 because of the chain rule, and we're going to be just left with cosine of 2x. And so it turns out that this integral on the left side anyways is just 1/2 x plus, let's see, 1/2 times this, so what, 1/4 sine of 2x. Awesome. So that's half of this problem solved. And the other half is just this one. And we can tackle this one in the same way, which is that I have cosine squared of x multiplied by cosine squared of x. And again, turning these into, sine, which is typically a good idea, right? If we go back to 1 minus sine squared of x, we're kind of just back where we started, which is we can't let u be cosine, I can't let u be sine, I can't let u be 1 minus sine, none of those work. And so here we're going to use power reduction on both of these, and I would turn this into 1/2 plus 1/2 cosine of 2x. I would turn this into the same thing, and because this is actually a homework problem, I'm not going to finish it, but you would just do some distribution. We're going to end up with some cosine squareds, and we would use the identity one more time to eventually get down to where we're doing integrals of like cosine of maybe 4x or cosine of 8x or whatever it is that we end up doing. But the important thing is they're all raised to the first power. And we can integrate trig functions that are raised to the first power, no problem. Okay. So far, this is all just kind of using u substitutions and or a little bit of trig knowledge. And so I guess maybe one more example just to say that I did it would be, I don't know, let's do an integral that involves tangent of x, and let's do like secant. Well, all right, so if we did secant squared of x, right, this one's a pretty easy u substitution because if u is equal to tangent of x, the derivative of tangent of x is equal to secant squared of x, and life is good because this will end up becoming our du. And then all we need to do is the integral of u because we've let u be equal to tangent. So I'm going to say let's spice this thing up a bit, and instead of doing tangent of x times secant squared, let's do times secant cubed of x dx. Okay, let's try this one. All right. So if we do this one, there are a couple of options for trying to handle this. So option 1 is we try and turn everything into sines and cosines, which is actually a pretty solid idea of something to do. If I write tangent as sine of x over cosine of x, and then I know that secant cubed of x is just 1 over cosine cubed of x dx, then this integral just becomes the integral of sine of x over cosine to the 4th of x dx. And at this point, I could go about doing a u substitution. I could say, let's let u be equal to cosine of x, not cosine to the 4th, because then the derivative gets more complicated. But this is going to give us that du is equal to negative sine of x dx, or in other words, that du over negative sine of x is equal to dx. That's going to substitute here. It's going to cancel out the sine, and we're going to get negative integral of 1 over u to the 4th du. And then this is just a simple antiderivative. We can get the answer in a second. So that one's not so bad. another example, or not another example, maybe option 2, I don't know. So I know for a fact, let's see, like what are some things I might try? So I know that since if I have tangent of x, its derivative is secant squared of x. So maybe I could try writing it like this, okay? Now, will this help us? I don't know, right? If we choose this and we say, let's let u be equal to tangent of x, the derivative of that is secant squared, but unfortunately, it's not going to allow us to cancel out this extra secant here, so we would be a little toast. So that doesn't work. Let's see, what's the derivative of secant? The derivative of secant is secant tangent. Oh, so if we write it in this particular way, I notice that I have kind of a spare secant tangent sitting here. And so if we decide to let's let u be equal to secant of x. Let's let it equal one of those guys. So this is going to make the derivative du dx equal to secant of x tangent of x. And this is going to lead us to the quick conclusion that du over secant of x tangent of x is equal to dx. And that we're going to, dx up there. We're going to substitute into our integral, and that's going to give us integral of u squared du very quickly, because the secant of x, tangent of x are going to cancel with that. And the answer to this one is we're going to have u cubed over 3. Oops, no more integral symbol if I've taken the integral, right? So u cubed over 3 plus c, and then we plug in what our u was, so we're going to get what? That's u is equal to secant cubed of x over 3 plus c. And so we could leave it like that. We could write it as 1 over 3 cosine cubed of x plus c, whatever it is that we want to leave it as. And you'll notice that this is the same answer as what we have before, because if we had finished this previous version over here, we would have gotten, right, this is negative the integral of u to the negative 4th du. To solve this, we add 1 to the exponent, divide by the new exponent. So we're going to get u to the negative 3 divided by negative 3, but that negative sign in the front is going to cancel. So we'll just have divided by 3 plus c. And then we remember that u was equal to cosine, and cosine to the negative 3 just drops it down into the denominator. So I would get 1 over 3 cosine cubed of x plus c. So we're going to end up at the exact same place. And you could leave it as secant cubed of x over 3 plus c if you like. That's a-okay. So what are some kind of general strategies in doing all of this? General strategies have to do with, if you're dealing with tangent functions, right? If you're doing integrals and there's tangents in there, we want them to kind of be paired up with some secant squareds of x. Or if you have an integral that has secant of x in it, we'd like it to be paired up with a secant of x tangent of x. And, very similarly, if we're doing integrals that involve, let's say like sine cubed of x or something like this, because there's a sine of x there, we would really like there to be just a cosine of x sitting somewhere in the problem. And as soon as we get one of those, we are good to go. Now, I don't want to say too much more than this because I personally think that doing these trig integrals is much more interesting and fun if you work them on your own, although the textbook does have some more examples worked out that you can go through if you feel a little dissatisfied with the amount that I have done here. But yeah, I think that's going to do it. This is a good place to pause for trig integrals. They're just integrals that specifically work with integrating trig functions. And they require a little bit of cleverness, whether it's recognizing u's and du's somewhere or using some of these identities that we wrote down earlier to help us rewrite the integral in a way that is going to be solvable for us. So that's going to do it. Hopefully this integral video wasn't too bad. And if you're feeling brave, head on over to the next one.